Hi everyone, I'm Ruizhe and you can call me Rui. I'm a research fellow in the Nottingham Biomedical Research Center. And today I will give a talk about some applications using the deep learning based image segmentation and registration technique in the 4D dynamic fetal MRI images. And let's just give a brief background of this talk. And this talk is based on a welcomely funded project called NIHR, and which target to detect the stillbirths using some new techniques. And nowadays, every 16 seconds, one baby is stillborn, which means the baby died before born. It ends up with more than 2 million stillborn babies globally every year, and it's a very big harm to both the parents and the wider society. So there is a very big motivation to optimize the stillbirth prediction method before the baby born or during the pregnancy. And as a part of the in-utero group, the University of Nottingham focused on the placenta contraction, and which has been identified as an important biomarker related to the stillbirth. And now we have multiple groups working on multiple type of data. For example, the physical group designed a device for pregnancy to monitor the movement of the placenta in real time. And the biophysical group and the math group views and model oxygen levels and transport in the placenta through the dissection and modeling. And of course, the clinicians collect some clinical information during the patient's pregnancy. And also, multiple 4D dynamic MR image is scanned at various stage of the pregnancy to observe the changes and development of the fetal and the pregnancy itself, which is I mainly focus on. And so today I'm going to talk about the deep learning based segmentation and the registration on the MRI data, the 4D dynamic MRI data. Okay, and this is an example of 4D dynamic fetal MRI data. As I mentioned above, it can be used to detect the stillbirth through monitor the placenta contraction. And moreover, it's not limited to just this application. It can also be used for various other important tasks, such as monitor the fetal health, tracking fetal development, and to identify the potential developmental issues. But the 4D dynamic MRI image is a very challenging data for deep learning models and some further analysis, since it's consistent with 3D volume with multiple time points, which makes it very large for analysis. And it also includes some complex movements, such as baby cakes and something like the heartbeats, which go beyond the placenta contraction. And both these two challenge add additional workload to the manual detection of the placenta contraction. And also, moreover, it's very time consuming to apply the manual annotations, such as the segmentation, such as segmenting the placenta and the baby in these 4D images, which limits the sequential analysis of the region of interest, or we call it masks. So to make a smooth contraction detection, we developed two methods. The first one is a segmentation-based method, and another one is a registration-based method. They both based on the 4D dynamic MRI image. And for the segmentation-based method, we trained a segmentation model to perform the automatic and accurate utero and placenta segmentation. Then using an algorithm to detect the contraction based on the changes of these segmentations, or we call it masks. And this method needs some manual annotation to train the model first. As we all know, the deep learning based method is a really data-driven method, which means when we got a large, high-quality data set, we can get a good model. But it's a bit difficult for us to do some manual segmentation on the 4D dynamic MRI image. As I mentioned before, it's a very large and complex data set. And furthermore, we developed a retribution model, which aims to minimize the human input. And the retribution model will be trained without any annotation, which can, as I mentioned, minimize the human work. And during the inference time, we can give it a 4D MR image with a mask for only one frame or single 3D volume. And then the model can automatically track its movement of the mask across all of the time points. And compared with the traditional retribution method, the deep learning-based approach, of course, as a feature of the deep learning models, it can significantly speed up the inference process and provide faster and more efficient results, even with data spanning large time point. Like for example, for using some traditional retribution method, for example, the aunt or something, it may take, for this large data, it may take 10 to 30 minutes for register one 3D volume to another 3D volume. But based on our developed deep learning-based retribution method, for example, we only takes less than 1 minute to register around 90 3D volumes, which is much faster. Okay, so let's go to talk about some details to both models. And firstly is the segmentation and the contraction detection. Okay, so for the image segmentation work, we employed one of the well-known models, which called NUNet, and we used the version 2 here, NUNet v2. And thanks for the MR group, they manually segment 169 3D volumes for 39 patients. And besides, they also provide more than 4,000 2D slices for validation use. So based on this data, we train a baseline segmentation model to both do the contraction detection and validate the retribution model, which I will talk about it later. Okay, so after the model training, we can say it achieved a relatively good segmentation result on the uterus and the placenta. Yeah, this is the numerical result. It's not bad. The death coefficient, which means 1 is a perfect segment, and now it's 0.93, 0.83, which is not bad for on both the uterus and the placenta. And here, just let you know, the green region is the red region is the placenta, and the green plus the red region is the whole uterus. As you can see, the segmentation quality is fine, and this is the 3D mesh, which looks good. And once we got the segmentation results, we can draw the curves, which shows the percentage changes of the volume and the wall length of some part inside the uterus, like the volume and the wall length for some of region. Yeah. And so next, when we got the curves, we can use it as an input to the contraction detection algorithm. And it's based on the gradient of the percentage changes. Yeah. So firstly, we smooth the original lines to drop some noise. We just select 3 lines here. The another 2 lines we already validated is not very important. And next, we detect the large gradient values, which indicate there is a And then after the smooth, we firstly calculate the gradient for each of the time points. And then we detect the large gradient values, which indicate there is a large changes of the volume or the wall length. And if there are more than 2 curves, you can see there are both 3 curves are agreed here and more than 2 curves agreed here, we will say, oh, there is a contraction. So we just detect the contraction here. And then, yes, no, that's the algorithm for this one. Okay, and the code is currently hosted on the GitHub as a private repo, and we plan to make it publicly available upon the completion of this project. maybe several months later. Not quite sure. Okay, and this is an example of the contraction. As you can see, during the red region, you can see there is a very clear contraction, and which also indicates the yeah, we already asked the clinicians that that's a real contraction here. So this is kindly, I mean, validate our method. Okay, so let's move to another part. The retreat model. Okay, so I believe most of you are already familiar with image retribution, but I would like to provide a brief introduction to the deformable image retribution to ensure clarity and avoid any misunderstandings. The image retribution is to align one image, we call it a source image, to another image, and we call it target image. So we align the source image to the target image. And for the deep learning based deformable image registration, firstly, we send these two images to the trained registration model to get the deformation field, and the deformation field is indicate how each voxel moves in moving image to match the fixed. You can call it source image to match the target image. We also sometimes we call it moving or fixed. I forgot to change it here. Sorry. To just how each voxel moves in source image to match the target image from here to match to here. And then the deformation field will be applied to the source image through a block called a spatial transformer. And we can get the warp image here, which is the aligned source image. Sorry. And it also need to be noted that we can apply the deformation field not only to the image. If we have a region of interest, or we call it mask, we can also apply the deformation field to the mask. So we can get something like this, a warped mask, we call it. And for some type of image, the warped mask can be used as the mask of the target image. So in this case, the registration model can do some work like the segmentation model, or it can do some segmentation work. So I think now we should know the deep learning based image registration process briefly. And let's move to the proposed movement tracking pipelines. And for this pipeline, the input is a 4D image with region of interest or mask for one frame, or for one 3D volume, we can also say it. And the output includes three things. The first one is the deformation field, as I mentioned before, which shows the deformation field shows the movement from the source image to the target image. And second one is the masks for all frames based on the input mask. Like I mentioned, for some type of image, it can do the segmentation task as well. And the uterus image, actually, yes, it can do this. And thirdly, the final output is the curves indicate movement of each mask. I will show this later. And there are lots of registration network nowadays. The one we use here is based on our previous paper, which can handle images with large deformation. And also the model, definitely the model should be trained for deep learning model. And the model is trained on unannotated paired 3D MRI image. As I mentioned, we don't need any mask. We just send the paired image to the model and it generates deformation field. That's what we use. So we don't need anything about the mask. We just need the paired image. Okay. So this is the pipeline. I will go through it step by step, but just very quickly go through it. Okay, firstly, we should apply a pre-processing to the 4D MRI image to fit it to the input format to the registration model. Include some resizing and normalization, something like this. And then we should draw the masks for one of the frame. For example, here we draw the uterus and the placenta for the frame Fi. The frame means the volume, only one time point. And next, we align the Fi to all of the other frames from F0 to Fn. And then, after we do we send them to pairedly send them to the registry model, we can get a set of deformation field. It will be a 4D one. So which indicates each of the frame, how it's aligned from Fi to another frame. And by applying them, as I mentioned before, we can apply the deformation field to the mask as well. So after we apply it to the mask, we will get a set of masks for all of the other frame. So we can, after we got this one, we will do some post-processing, like resize or something to match it to the original image. And then we can generate some final report here. Yeah. And that's the whole process of the registration pipeline. And let's revisit the input and output of the image. We only need to input the 4D image with one frame of masks. And then we can get the deformation field and also the masks for all of the frame. And we can also get some curves indicate the movement of each mask. And also it's worth to mention that if we didn't input any masks, just input the 4D image itself, it can also generate the deformation field. Because we don't need input any mask to generate this one, as I mentioned. We only need to input the paired image. And also we can generate a curve which indicates the global movement of the whole 3D volume without any mask. It may be sometimes we can use it in some tasks. I'm not quite sure for now. Yeah, and there are two examples for the registration pipeline, and you can see these two examples. They use the same 4D MR image but with different masks. The left-hand side one is the mask is the uterus and the placenta, and the right-hand side one is a mask of the baby. This mask is manually drawn by me, so it may not very accurate. So let's just do a example. So this is height, you can see, and there are some body part, arms maybe, leg. I'm not sure which part is leg. So this is the movement tracking report for both the segmentation model and the registration pipeline. You can see definitely based on the 4D MRI image, so there will be some, you can see some movement during the whole process. And I think it's close to the contraction. Yeah, contraction, you can see there is a big movement. Okay, so and the first one is based on segmentation model, and the remaining one is based on the registration model. I think it's quite interesting to see the result from both models match to each other. You can see there is a contraction here, and if you look at the registration curve, which track the movement, you can see there is a big movement here, 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 and here. Yeah. And also this one, the final row shows the movement of different part of the baby. You can see for different part, the movement are different. The red region only small, very small movement, maybe not very clear here. But I will give the slides to you later. I think it's gonna be simple to see. And for some region, you can see different regions have different movement. And also, the red box is a very interesting thing. This is the baby cake, which is identified by the clinicians. And you can see from the segmentation curve is not very clear. They just you can see there is a movement, but not very identified movement. But here you can see there are two curves very different. So I think it's going to say something. And but we didn't do much further. Further experiment on this. But I think there is this curve at least tell us it can do some potential work, such as monitor the baby cake or something. Okay. So as an output, we have developed a website-based tool which include the segmentation, registration, and contraction detection function. And the code now is hosted on GitHub as well. As I mentioned before, we plan to make it public available after finish the project. Yeah. So this is that's all of the two methods. So this is a summary of today's presentation. We developed an automatic segmentation model for the utero and placenta segmentation, and also the contraction detection things which can be achieved through the volume and wall changes. Thirdly, we also build a registration model to do the segmentation task and also the movement tracking. And currently, it's just optimized for the fetal MRI data, for the fetal MRI data. And I think it can also be very simply adapted to other 4D MRI types as well. And finally, we designed a website to include all of the functions and also the model parameters or something we will both upload to somewhere to be easily used. Okay, yeah, that's all. Thank you. So any questions?